Okay, so now for this problem, we have an answer for this one, and let's try to get that answer by solving for this. And we have two equations, right? Or three equations that are actually linear equations, and in that linear equations there's an intersection that will form a triangle, and inscribed to that is a square or a rectangle. So this problem asks for the largest area that can fit inside that triangle. So when we say inscribe, I would like to give some short English vocabulary for this subject muna. So when we say inscribe, it is fitting, let's say, an area to a larger area wherein the smaller area is the maximum area. And if we're talking about the volume, then we're fitting a certain volume of a smaller object inside a larger object that would maximize the volume of the smaller object. So just to give you an example, if we have a circle and then I want to fit something like a triangle inside of it, so I can describe this as the triangle is inscribed in a circle. With that, we know that the maximum area of this triangle is of our concern. And basically, what's constant here is the radius of the circle, because it's kind of, fixed. And the variables that are in consideration would be the dimensions of the triangle, because it is the thing that we need to maximize. So this figure can also be described as the circle circumscribing a triangle. It can also be described in that way. So there are two ways that we can describe this. Again, the triangle is inscribed in a circle, or the circle circumscribes a triangle. So hindi yun circumcise, ha, baka may circumcise na naman dyan. So yun yung two definitions that we can give to this figure. And the difference between circumscribed and inscribed is that the thing that we need, the constraints that we need to be, that needs to be set constant. So if we are circumscribing a certain figure to a smaller figure, then the fixed variable is, the fixed parameter in that way is the dimension inside, or the dimension of the figure that is on the inside. So if it's circumscribed, we can just say that the fixed parameter is, that's a very messy handwriting, let's just do this. So if it's circumscribed, I'll just be doing some subtitle here. So if it's circumscribed, then we know that the fixed dimensions are the dimensions of the shape or the figure inside. And if it's inscribed, then the constant parameters that we'll be using are those for the larger figures or the larger shapes. So in this case, if it's inscribed, then the fixed one here is the for the circle. And then, for example, if we have, let's say, a square, and then we wanted to or let's say a cube, and then we wanted to fit a sphere inside of it, so I could also say that the sphere is inscribed a cube, and then in that way the side of the cube is fixed. Or if I would be describing this as if the cube circumscribed the sphere, then I know that the radius of the sphere is kind of fixed. Okay, so that's how it works for our simple mathematics. Now let's try doing this. So it's inscribed, therefore we know that the dimensions of the triangle is quite fixed. And to do this, let's first illustrate the problem. So we know that we can form three lines from this equation, and we know that y equals x is simply a diagonal line that that can be drawn from the center and just doing 45 degrees. So for y equals 0, we know that y equals 0 is certainly the x-axis. So in this case, let me just use green for this. So that's x equals 0. Okay, let me just thicken our lines. You can see it clearly. Okay, better. So we have those two lines. So let me just give names to this. This is y equals 0, and then this line right here is our y equals x. And then finally, we need 3x plus y equals 20. So I'll just be using the intercept. So if we use the intercept here, then we know that if x equals 0 in this equation, if x equals 0, we know that y equals 20. And if y equals 0, we know that x is equal to 20 over 3. Okay, so 20 is quite a large number, so let's just use a very short intervals for this. So 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, that's 20. And then let's do 20 over 3. So 20 over 3 is 6.67. So let's have 1, 2, 3, 4, 5, 6. That's around there. And then let's just trace the line. I'll be using something like red for this. So I hope I made the correct line. So that's it for our, let's make it past 20. So that's it. So the rectangle, the triangle that is of our concern is this this one, 1, 2, 3, 4, 5, 6. So it should be like around here. Okay, so this is our triangle of concern, and we need to find the largest rectangle that can fit in to this triangle. And it says also in the condition that one side sits on this x-axis, so it's like this one. What could be the area of that rectangle? Rectangle. Okay, so I'll be zooming out. So I think you already understand how this problem works. So that's it for our rectangle, and then we need to find the area of that. So we know that the area of the rectangle is always something like length times width. We know that this could be the length, and then this one is the width. So that's simply the area of the rectangle. But how do we express that in a certain single variable? Because that's the next step that we should be doing. So if you would look closely on this, and I'll be zooming this in, something like this, okay, and something like this. Okay, so this rectangle, or let's just use this one. So we know that this rectangle is actually touching or tangent to any, or it's touching the lines. This one is the 3x plus y line. Let's use red for this. So it's touching the 3x plus y equals 20 for one side of the length, and then the other side would be for y equals x. And then finally it sits on this y equals 0. So if we can represent that in a way that if this is actually the, let's use another color. So if this is our width, we can just say that this is the y value, because at any point on the Cartesian coordinate system, we know that this length has the same height as, this point has the same height as at this point. So whichever the value for y is, that we could always say that the height will not change from this point to this point, and that's just simply y. So we could just say that the width is equal to y. But how about the length? So in this case, since I've related this w in terms of y, now I need to relate this L as a function of y. But we know that this distance, because we're talking about the length, in this case, because our length is simply a horizontal segment, we can just say that the distance is simply the difference between the x sub 2 and then x sub 1 of these x values that we have at this point. So if I have, let's say, x sub 2 right here, and then y sub 2, and then this one is x sub 1, y sub 1, wherein we know that y sub 2 is equal to y sub 1, then we're left with x sub 2 minus x sub 1 being our distance. So in this case, the length is x sub 2 minus x sub 1. But in our equation, x sub 2 can also be represented in terms of y because that is x sub 2. This is the line of x sub 2. So if you have any value of x that's right here, if you want to express that in terms of y, we could say that y is equal to 20 minus 3x. Okay, so that's the case for our equation. And then if we want to express that in terms of y only, then we could just do something like 20 minus y over 3, and that is equal to x. And that's exactly the thing that we need here. We need the x expression in terms of y. So that is 20 minus y over 3. And then for our x sub 1, we know that y is equal to x. So for every x, there's just an equivalent y. So if you have a y value here, we know that for sure that the value for that is x. So we know that that's just minus x. And now we can express this in terms of our area of the area of the rectangle. So that is a rectangle that is equal to length times width, which is in which the length is 20 minus y over 3. And then I actually forgot to change this. So we know that x is simply equal to y in this case. So let's just use y. Okay, so we proceed. So we know that that is minus y, and then we multiply this with the width, so that's y. Okay, so that is the area of our rectangle. And then we know that if we take the derivative of this expression in terms of y, because that's our single variable, so we can determine the critical point if we would equate that to 0. So the derivative would be simply 20 minus y over 3 minus y times 1, and then plus y times, we get something like 1/3, I think, and then 1/3, and then I think that should be negative 1 for our derivative, because we could just factor out 1/3 from here, and then we differentiate 20 minus y. So that simply leaves us negative 1, and then we have minus 1 right here. So therefore, a prime of y is, you can simplify this further, so I'll just be doing that. And then plus, we have, I think that's 1/3 minus 1 minus 1. 1/3 times negative 1 minus 1. So that's just negative 1/3 and then minus 1. So that gives us negative 4/3 y. Okay, so that's our derivative is actually 20 minus y over 3 minus y minus 4/3 y. And you can also simplify this further, but from here on you can actually equate that to 0 and find the value of y. But for this sake, I'll just be simplifying this, because I don't know, Einstein may get angry. Joke. So I'll just continue simplifying for this one, and then I would equate this to 0. But you can always do that starting from this. So you can now obtain the value of y, and you should be obtaining a value that is equal to 2.5. Okay, so in this case, we know that y is 2.5. So basically, this width is 2.5, and now we're left with the length. And the thing is that we need to just check on the area, and if that is really the largest area. So if we would just plug in this back to our original equation that we know, this one, we could just say that the area would be 20 minus 2.5 divided by 3 minus 2.5, and then we multiply that to 2.5. So this is our area, or the largest area that can be inscribed in that particular triangle. So you should be getting a value that is equal to 25 over 3. So the unit is actually square units. Okay, so that is our area. Now, in this problem, the answer is actually 20 over 3. That's actually a typographical error, so bear with it. This should be 25 over 3 square units. And now that we've already obtained the answer, we could check on that if that's really the maximum area. So remember, this is the first derivative. You can take the second derivative for this one and then substitute this 2.5. Since this is positive, we should be getting a negative answer. So if we'll be able to get a negative answer based on this critical point, then that is actually our maximum. So let me just do the differentiation right here. So that will be 1/3, and then I think that will be -1, and then we have a -7/3 for this particular equation, and then that's it. The derivative is actually a negative value, and we don't have to like substitute this anymore, this function. So that is negative. So basically this is the correct answer. And now you can always check on that using the first derivative as well, the one that we do something like number line. If you could just remember that you have 2.5 here, and then check on the values that are at the left of 2.5 and then at the right. So you substitute that with the derivative, and you should be getting, for the left side, you should be getting positive, and then this one should be negative. That's why you can draw a hill, and we know that that 2.5 is the maximum. So that's it for this problem. That's fairly easy if you could just understand how these things work, but it gets really difficult when you try to do different things here, like I actually presented in a face-to-face class the solution for this having something like similar triangles. So we started with something like this, I think, and then the larger portion of the triangle, and that's a fairly very long solution for this. So I just presented you the shortcut or the fastest solution because I think that's the, I think you need it more than the other solutions that are very long and tedious. So this is how it works. We used analytic, actually, if you could just notice, we're doing analytic geometry since ever since the first problem started. So that's it for this kind of problem. And now let's move on with another problem that might be involving your solid geometry.